let's look at a couple of examples that involves the dependent sources. And one is for node voltage analysis, and then the other one is for mesh current analysis. And let's look at the first one here. We have this. This is the voltage source, but this is a controlled voltage source. This voltage source is controlled by a current, right? So this is the current, and this is the controlling current. So this is the controlled voltage source, but still voltage source, okay? So this is probably the most confusing part for many students. You label the IX here, but the 10 here is, we call this as the transfer impedance or transfer resistance. So in this case, this 10 has the ohms, so therefore it's still, you get an ohm times the current, you still get a voltage, right? So this still voltage source, and IX is the controlling current. And those kind of control sources typically is used to model the physical system, because in the actual physics system, it's very rarely you have controlled voltage source. It's typically we use this to model the physical system. Or the physical components. And in this case, you just when you write the equations, you just treat this the dependent source as independent first, and then finally you need to get rid of this controlling source, right? So by relating that with the voltage source in this case, with the node voltages, and let's do that. Just show what the steps would be. Let's see at node number 1. And node number 1, the equation here, I still write the KCL equation, remember? So in this case, I still have V1 over 5 over S plus V1 minus V2 divided by 3 ohms. That's equal 2 over S. So the first equation is good. We don't need to do anything for that. And the second equation here is the second and node number 2. We have V3. We have V2 minus V1 divided by 3 ohm. That's the current leaving through that 3 ohm resistance from node number 2, plus the current leaving from node number 2 through this 2 ohm resistance, plus the current leaving from the node number 2 through that 3S impedance. That's equal to 0. The current entering from the source is 0. And node number 3, so this is the node number 2. And node number 3, we can't really write the KCL equation, right? Because we have a voltage source there, although it is a controlled voltage source. But still, we can use V3 is equal to 10 I sub x. And here we don't really like the I sub 10x, I sub x in the equation, because it's another unknown, right? So we want to have the only unknowns. We have the node voltages as the only unknowns. And what we do is we can write the I sub x. We also write, so this is the kind of the things we had. We're treating the controlled voltage source just as the independent source. Then we write this equation, but we try to get rid of these. How we can get rid of these? We recognize I sub xs is equal V1 s minus V2s divided by 3. So we can substitute this to the third equation, right? So therefore we get a V3 is equal 10 times 10 times v1 minus v2 divided by 3. So we can move things to the other side. So in this case, we move to the left side. So this equation here, we do another step here is v1s over 3 plus v3s minus, oh, I have a 10 here, and times and minus 10 over 3 times v2s, right? So this equal to 0. So we're gonna have this, the first equation, the second equation, and the third equation now. So we only have the node voltage as unknown. So we can solve these equations, 3 equations, okay? So that's how you deal with the control voltage source in the node voltage analysis. Let's look at another case. We have a control source of a mesh current analysis. So in this case, this is the controlled source or the dependent source. This is the controlled current source. So this controlled current source could be controlled by a voltage or could be controlled by a current. But in any case, this is a current source. Right. We use an arrow for the current source. And here may be confusing. So I label point 1 times Vx. And here the controlling Vx is the controlling voltage. That means this Vs controls how much the current source would be. And in this case, this is the current. That means that's the conductance, right? Or transconductance. Transconductance or transadmittance, if it is a complex. It could be complex also. It could be a function of S. In this case, I only have the real number, 0.1. So that's the transconductance. And so in this case, just as we did for the node voltage analysis, we just treat this dependent source as independent first, and then we're trying to figure out how to get rid of that controlling voltage or controlling current, right? So in this case, let's see the mesh 1. So mesh 1 and mesh 2, oh, we still need a super node, right? So we don't really have because this current source is shared by 2, so we still need to have this super mesh. And the super mesh, we write the voltages. So the voltage here, the voltage drop across each, we still have 5 over S times I1 plus 3 times I1 minus I3. And for the 3S, so that's 3S, I2 minus I3, and that's equal to the voltage rise, which is negative 12 over S, right? Because this voltage drops here if we following the reference direction we chose for the super mesh, and the I1 and the I2 are related to each other by I1s minus I2s is equal 0.01 Vxs, V sub xs, right? So this is the relation between these two. This is actually the relation between the element current and the mesh currents. And for mesh number 3, we can write the equation just as we did before. So we have let's start with the 3 times I sub 1x, I sub 3x, s minus I sub 1s, and plus 2 times I sub 3, and plus 3s I sub 3 minus I sub 2, that's equal to 0, right? So the second equation here, we need to get rid of these. And this one here is, we know this should be, so the Vx S should be I3, should be 3 times I3x S minus I1s, right? So we just need to substitute that back into the second equation. So the second equation, we substitute this in. So the first equation and the third equation, we don't need to do anything. So this is the first, this is the third. So that's good because they are all in terms. They are all they have the 3 unknowns, right? So using the mesh current as unknowns. So for the second one here, I'm writing I1 minus I2 is equal point. So that's 0.1 times 3 I3 S minus I1s. So let me move to the other side. Let's see if we can get this. So I1 here, I got a 0.3. So I get 1 plus 0.3 for the I1, right? And for I2, I got a negative I2s. For I3, I got a negative 0.3 is, I3s. That's equal to 0. So this is going to be our second equation. So we combine the first, second, and the third. So now we are having our equations with 3 equations with 3 unknowns, right? So in summary, if you have the dependent sources, you just first treat them as independent source. Just recognize them as one of the cases, maybe the basic case, maybe the one of the scenarios that's more complicated. And then you write the equation and then replace that controlling source, right? Controlling current or controlling voltage by the node voltages or the mesh currents, so that you end up with the equation that with node voltages as unknowns or mesh currents as unknowns only. Okay, I think that concludes all the different topics I want to cover for this lecture. It's been long. It's more comprehensive than what the text covered. I hope you enjoyed that, right? So remember, no matter what you do, just keep going and never stop. I'll see you next time.